So again, this is going to be done based on a single sample. I told you that we can take as many samples as possible from the population. Every sample is going to have a set of observation, and the set of observation that you got from sample is going to be different from sample to sample, but the sample size is same. You're not going to be changing the sample size. The sample size is a fixed number, and you are going to be picking a sample of size n using the simple random sample technique or SRS method. Since the observations are going to be different, varying from sample to sample, your X bars are not going to be the same. X bars are going to be different. So you will have the collection of X bar, and once you put all the X bars on your horizontal axis, you see that it's going to give you a normal curve. The center is going to be the same. It's not going to be changing. But what happens on either side, you have the variability. The variability is the one that's going to be different. That's right. Now, the second half of the central limit theorem is you are going to test the statement on mu. So basically, you are going to test the sentence or the statement on mu, or you can also call that as the claim. So that is what is discussed in testing of hypothesis. And this process is also done based on a single sample. All right. So here I'm going to say the two branches again. One is the confidence intervals. So our goal was to find the probable limits for mu based on your confidence level, which is C, and when sigma is known, you got the two numbers. So using the formula, you see that. But in the second half, the testing of hypothesis, you are going to assess or you are going to look the evidences provided by the sample data about some claim or sentence or the statement regarding the population mean mu. So basically, the definition of a hypothesis in English dictionary, it says educated guess. That is correct. So the educated guess is going to be on mu, the population mean. So the statement is going to be tested in testing of hypothesis. That is correct. To do this, we are given a test procedure. So here is the test procedure. For any test needs a test procedure. If it is a test, that means there is going to be a recipe or the test procedure will be there. The same way here, for testing the population mean mu, we are given a test procedure. So let's go over step by step. So you are going to define two types of hypothesis. One is called the null hypothesis. The other one is the alternative hypothesis. The null hypothesis is always going to be defined as H sub 0 equal to, again, I'm telling you, this is the recipe. We are going to be following this recipe to do the problems given to us, okay? And everything is the notation. You are going to be using this for the first time. So the concept is going to be, a bit harder to understand, but when it comes to the problem, it's going to be easy peasy. All right. So just hang in there, follow the recipe. Null hypothesis is H sub 0 mu equal to any number coming from the population that I'm denoting it as mu sub 0. And you are going to identify the claim. That is right. We will talk about this later. So don't worry about this part. Identify that claim. Right. All right. In statistics or in math, if we have a statement, then opposite to that or in negation to the equality sign in math, we are given three signs. What are they? One is going to be less than, the other one is greater than, and the third one is going to be not equal to. So if we have the equality sign, then in negation to the equality sign or opposite to that sign, we are given three signs. It could be less or it could be greater or it is a not equal to. When I say not equal to, it includes both less than and greater than sign. That's right. So now I'm going to define my alternate hypothesis. So the alternate hypothesis could be, as I said, less than. That means mu is going to be less than mu sub 0, and that is given a name. It's called as a left tail test. And the second one I said, it could be mu greater than mu sub 0. And that is also given a name. It's called as a right tail test. The third choice given to you in math is mu not equal to mu sub 0. That is also given a name. It's called as two-tailed test. So if I mean to say two-tailed test, your mu could be less than mu sub 0, or you can say that it's going to be smaller, or it could be bigger than mu sub 0. So the null hypothesis is defined as mu equal to mu sub 0, always equal. Always equal. We are not going to play with less than sign, greater than sign, not equal to sign in your null hypothesis. So the null hypothesis is always mu equal to mu sub 0, and your alternative could be one of the three. Not all three, it could be one of the three. Mu less than mu sub 0, or mu greater than mu sub 0, and mu not equal to mu sub 0. So this part is new. Defining your null versus alternative is going to be new to you. And each one is given a name. If it is a less, that is called as a left tail test. If it is greater than, it's going to be called as a right tail test. If it is not equal to, then it's going to be called as it includes both mu less than mu sub 0 and mu greater than mu sub 0. All right. The step number 3 is you are going to bring your z-score that you studied in chapter 13. So I have written that here. Z-score equals x bar minus mu sub 0, because the value taken by mu in your null hypothesis, over sigma over square root of n. So this is the z-score, or this can also be written as square root of n times x bar minus mu sub 0 over sigma. So this is the formula. I'm just flipping, or square root of n in the denominator goes to the numerator, but don't forget to put the parenthesis, otherwise your syntax will be wrong. So this is going to be the z-score formula that I'm going to be bringing from chapter 13 in chapter 14. All right, so this is not new to you. We have already worked on this one, okay? And I told you that this is the application of the central limit theorem for quantitative variable. All right. So chapter 14 is the application of the central limit theorem for quantitative variable. Chapter 19 is the application of the central limit theorem for qualitative variable. So we have the application for quantitative variable given in chapter 14, application of qualitative variable given in chapter 19. So that way you can remember how the application is studied in the following two chapters after 13. All right. So x bar is the sample name. Mu is going to be the value stated in sub 0, the null hypothesis. And the next one is going to be step number 4. You are going to define a new concept called as level of significance. In chapter 14, in the first part, or under confidence limits, we introduced the term called confidence level, and we always maximized that number, say 90%, 95%, or 99%. So contrast to your level of confidence or confidence level number, here we are going to introduce the level of significance. So the level of significance is nothing but the complement of your number that you used in chapter 14 in the first part. All right. So this is the new number that we are going to be introducing, and alpha, it is denoted as alpha, and alpha is another Greek letter that we are going to be using here. And what is alpha? Alpha is probability of rejecting the null hypothesis when it is true. Everything is new, but as we progress, you will understand everything. Okay. So that's why I'm spending 2 days, today and tomorrow, on this material. Okay. So now, what is the probability of a type 1 error? So again, the type 1 error, we will be discussing it later, but here I'm just introducing the definition of alpha, the level of significance. So the alpha is defined as a probability of a type 1 error, and the event is there, and for that event you are going to attach a number. That's what we call it as the probability. Like your confidence level is going to be, say, 95% or 90% or 99%. I told you that it is going to be complement of that number. So when the confidence level is a 95%, then your alpha, the level of significance, is going to be 5%. That means the confidence levels and your level of significance, they are going to be complementing each other. When the C level is a 90%, your alpha is going to be 10%. When the C level is a 99%, then your complement of that number, which is going to be called as alpha. All right. So here you can see the diagram, what I mean by alpha, what I mean by 1 minus alpha. So if my 1 minus alpha is known as the C level, then your alpha, the level of significance, is going to be called as alpha. All right. So what is going to be your single tail test or the two tail test? So this is how this alpha over 2 is going to be if it is a two tail test. So for the two tail test, this is what you are going to be having for the two tail test. So this is going to be the center, mu sub 0, and this is going to be mu less than mu sub 0, and this is going to be mu greater than mu sub 0. So for the two tail test, I told you that your alternative hypothesis is mu not equal to mu sub 0, so which includes both mu less than mu sub 0 and mu greater than mu sub 0. That means the area is going to be given on both ends. So just follow whatever I'm saying here. As we progress, when you go over the material as a whole, you will understand everything. Okay? Right. Let's define what is the type 1 error and type 2 error. So let's see that. So in any decision-making problem or in any statistical problems, there are two types of errors. That is, you cannot avoid those two errors. So those two errors are going to occur typically in every single decision-making problem. They are called as type 1 error and type 2 error. So what is the type 1 error? So you are going to reject the statement when it is true. You are going to reject the statement or H sub 0, the statement on mu, the statement on mu when it is true. That means the true statement is rejected. What is the type 2 error? The type 2 error is you are accepting the wrong statement when it is false. So these are all the two types of errors that is inevitable in any decision-making problem. Again, the type 1 error is you are accidentally rejecting the true statement, or you end up accepting the wrong statement. That's it. So these two are called the two types of errors. Let's see some example here. So what is the example? So this is the example that I'm giving you. Let's consider an example where the statement on my null hypothesis is the defendant is innocent, not guilty. The alternate hypothesis is the defendant is not guilty. Not innocent or guilty. So the evidence is presented in court by the prosecutor, and based on the evidences, jury decides the verdict innocent or guilty, obviously. If the defendant is convicted, but he or she did not commit the crime, is type 1 error. If the defendant is acquitted, then he or she did the commit the crime is going to be called as type 2 error. I guess now you are getting the idea of what I mean by the type 1 error and the type 2 error. Let's put the same information in the table. That is correct. So I am going to call the convicted, acquitted, and then here on the other side across the table, I'm calling it as innocent, not innocent. So when you were innocent guy, acquitted, that's the correct scenario. Nothing wrong. Innocent guy, he's acquitted. That's correct. And not innocent, right? And he is convicted, that is also a correct decision. So no question about that. So he did something wrong, is behind bars. That's correct. He did not do anything wrong, he is out at large. So those two are the correct scenario. Nothing wrong, no comments. But what if the other case? The guy is convicted and he is innocent. So good guy did not do anything wrong. He is behind bars. So that is going to be called as the type 1 error. That's happening. We are seeing it. I don't want to go into that. But now, recently we have seen that incident. So we can understand this type 1 error. All right. I don't want to go deeper into that. How about the other one? The other one is he is not innocent. That means he is a guilty guy but acquitted. Now he is at large. He did something bad, but he is still at large, right? So that is going to be the type 2 error. So however careful we are, these two types are not going to be avoidable, or these two types of errors are inevitable in any statistical problems or in any decision making problems. So those two are called the type 1 and type 2 error. So in my technical words, I'm going to translate this type 1 error as, so what is the type 1 error? The type 1 error, I'm going to write it as, without the probability, the type 1 error is going to be rejecting null hypothesis, rejecting the statement, rejecting the null hypothesis when it is true, when it is true. So this is what I call it as the null hypothesis. Now you can see that from the table. Rejecting the null hypothesis, in terms of my technical words, I'm saying rejecting the null hypothesis when it is true is called as type 1 error. What is type 2 error? So the type 2 error is going to be accepting, or you can say do not reject. Because I have little room here, I'm writing it as accepting the null hypothesis when it is false, when it is wrong, or when it is false. So these are the two types of errors. So the rest of the two scenarios you can totally ignore because they are 100% correct. Correct decision, I'm not bringing it up. But I am just bringing the two types of errors that is inevitable. So rejecting the null hypothesis when it is true, when I attach a probability to that event, and that's what is called as my alpha, and alpha is going to be 5%. So when I am making a mistake, I don't want to maximize my mistake because it is a type 1 error. When I am committing some type of errors, I don't want to maximize that. So that's why I am trying to keep that number as minimum as possible, starting from 5%, or you can say 10% or 5% or 1%. So those are all the numbers that I'm giving. I told you that the level of significance and your confidence level are two contradicting numbers. So they are complementing each other. So when I'm maximizing my confidence level, when I am committing a mistake, I don't want to give a bigger number to that. So I want to keep the number as low as possible, as minimum as possible. So that's why I'm going to put my alpha as 10% or 5% or 1%. So again, this is a fixed number and it should be given in your problem. The alpha should be given in your problem when it comes to the testing of hypothesis. When it is your confidence limits, or you should be given the confidence level, say 90% or 95% or 99%. Okay, maximizing my confidence level is contradicting number two, the minimizing my error. I don't want to maximize the error that I'm going to be committing. I don't want to maximize the type 1 error. I don't want to maximize the type 2 error. I want to keep it as low as possible. So that's why my alpha is 5% or 10% or 1%. So that is the number I'm defining in step number 4. And it is usually those numbers. All right. So now the next one is going to be, so we can see that generally we assume alpha, the probability of a type 1 error is a 5% or 1%, unless it is given some value different from 5% or 1% in the problem. I'm reading this sentence. Okay, so it is usually 5% or 1% unless otherwise is given in the problem. Some other number given in the problem. All right. The next one is step number 4, which is the p-value. What is the p-value? So the p-value is going to be your probability value that is going to be obtained from the z-score, because in here you already defined your z-score based on your problem. That's right. So the z-score is going to give you the probability value. That's right. So that's what is going to be done in step number 4. So find the p-value. The p-value is defined for a single alternative hypothesis in a different way. But you are not new, all familiar with this one. Okay, when it is a left tail test, it's a 0 tail test. P-value is going to be, as always, normal C. So that negative sign is not the takeaway sign, the tiny negative sign given in the last row. That's going to be the tiny negative sign, comma, the z-score, and that's going to be your left tail test. So here is the diagram for that. And if it is your right tail test, then you are going to be using your p-value is equal to normal CDF. It is going to be z-score, comma, my favorite number 8. If you do not like 8, you can put any number of your choice. I hope you remember that I introduced in chapter 11. Your break can be any number that could be below 8. It could be -4 or -5, -6, -7, -8, -9, -99, -99999. Any number of your choice can be written as the lower boundary. When it comes to the right tail test, then you are going to have the z-score, comma, positive A. So that is the value. Nothing new. We have already seen this in chapter 13. All right. When it is a test, when mu is body is sub-0, I told you that this will include both cases. You need to have the probability on the tails. So that's why I'm writing it as 2 times normal CDF z-score, comma 8. If your z-score is a positive number, or you can write it as -8 comma z-score if the z-score is a negative number. All right. But it's going to give it can two z-score the score two times normal CDF. It's going to be negative z-score. Yeah, it's going to be negative 8 comma the score, the z-score in this case is going to be a negative number. That's right. All right. Now let's see the probability. All right. So the next one is your alpha. The other probability value is your p value that you got based on the sample data and the z-score. So now I have the two probability values. So now I'm going to be comparing the two probability values. What is the conclusion that's going to be written? If your data is giving you a smaller p value, if your probability value is going to be smaller than alpha, you are going to reject your null hypothesis. So smaller the p-value, you're going to refute your null hypothesis. And you're going to say that the data is not statistically significant at the given level alpha. If your p-value is greater than alpha, stronger the p-value, it means we do not reject the null hypothesis. So stronger the p-value, we we fail to reject the null hypothesis. All right. So smaller the p-value, if your p-value, the probability value that you got based on the sample data is less than or equal to alpha, you are going to reject your null hypothesis, and stronger the p-value, you fail to reject the null hypothesis. So maybe I can put, because I wrote it as a sentence, stronger the p-value, I am going to say fail to reject the null hypothesis. Do not reject means fail to reject. Fail to reject. That means we do not reject the null hypothesis. That means we are going to keep the null hypothesis. So again, you are going to compare the two probability values here. Smaller the p-value is less than or equal to alpha, you reject the null hypothesis. Whatever statement that you have on your null hypothesis, that's going to be refuted. But on the flip side, if you have a greater p-value, stronger p-value, if your p-value is greater than or equal to alpha, you fail to reject your null hypothesis. So this is the conclusion that's going to be written. So this is your example here. So your alpha is going to be, usually I told you 5% or 1%. So that is the probability, that is the area, and your z-score. So this is going to be the z-score in your right-tail test. So this is the right-tail test. If a z-score is a positive, then you see that your p-value is greater than or equal to alpha. So this is your alpha. Alpha is going to be the red zone. All right. Alpha is going to be the red zone. And that's going to be usually 5% or 1% probability. That number is also going to be given in your problem. So this is what I call it as the rejection zone. The rejection zone. Rejection probability or the rejection region. You can call that as rejection zone or rejection region. in this case, I have a stronger probability. That means I am going to keep my null hypothesis. So this is going to give me fail to reject the null hypothesis. Fail to reject the statement on mu. The statement on mu. All right. What is the other diagram? The other diagram, my alpha is a bigger region. So this is my alpha. This is my alpha. I need to use the red color. This is my alpha. This is my alpha. And where is my probability? The probability is going to be here. This is the probability, and the probability is going to be falling in the rejection region because this is my rejection region. Rejection region. Since my probability value is a tinier number, it is falling in the rejection region. That means my hypothesis is going to be rejected. So here you are seeing the scenario where your p-value is greater than alpha. So here the probability value, p-value is greater than alpha. The probability is bigger than alpha. P-value is greater than alpha. All right. So here your p-value is going to be, the probability value is less than alpha. It's less than alpha. Right. So this is also your right tail test. This is also your right tail test. And since my p-value is falling in the rejection zone, so what is the conclusion? I am going to be rejecting the null hypothesis. So reject the null hypothesis. Or you can say the statement on mu is rejected. On mu that you defined in your null hypothesis is rejected. So this is what I'm going to be comparing the p and alpha. I guess you understand what I mean by that.
I understand that.
Yeah. So maybe if we do one or two problems, you will get a better picture of what I mean by. So I have also given the other diagram where I need to say the rejection region, which is going to be alpha, and this is my alpha. I guess you see the tiny alpha here. So if my probability is going to be greater than, in both the cases I talked about the right tail test. So here in the next picture you see that. Okay, so it all depends on where your probability value is going to be falling, whether it's in the right or rejection region or in the acceptance. The complement is going to be the acceptance zone. All right, so one more time, I will recall the recipe and then I will jump into the problem because we don't have much time, okay? All right, so again, you are going to define the two types of hypothesis. One is the null hypothesis, the other one is the alternate hypothesis. And the null hypothesis in this math 130 level, it's always going to be mu equal to mu sub 0. And you are allowed to play with the one of the three, not all three, one of the three, which is mu less than mu sub 0, that's called as a left tail test, and mu greater than mu sub 0, that's called as a right tail test, and mu not equal to mu sub 0, and that's going to be called as the two tail test. Each one is given a name, okay? If it is like your letter L, you tilt it, that's going to be the less than sign. So that is your left tail test. Left, less, everything is beginning with the letter L, so you can remember what is the left than, left tail test and everything. And the opposite of left tail is going to be the right tail test, which is going to have the greater than sign. And then the third one is going to be the two tail test that includes both the left tail test and the right tail test. Okay. And the next step, you are going to define your z-score. The z-score is given by the formula. Remember the chapter 13 z-score. It is because you have a sample of n observation. The sample data is going to give you the sample mean. So it's going to be square root of n times x bar minus mu sub 0 over sigma. And you are going to define the new number called alpha. Alpha is usually 5% or 1% or 10%, unless otherwise some different number given in the problem. And you're going to define your p-value. So the p-value is going to be calculated for your left tilted, it is going to be normal CDF negative 8 comma z-score. And for the right tail test, it's going to be z-score comma 8, right? And if it is a two tail test, it's going to be 2 times the normal CDF z comma 8. If z-score is a positive number, and it's going to be negative 8 comma z-score if it is going to be a negative number. Let me also put that tiny negative sign within parentheses. That way you will remember the tiny negative sign is given in the last row of your calculator. Okay, that is a tiny negative sign that's going to be used. Do not use the takeaway sign. All right, so then you are going to compare the p and alpha. If p value is falling in your rejection region, you're going to reject your null hypothesis. If p value is falling in the acceptance zone or other than your rejection zone, that means you are not going to reject your null hypothesis. So that picture is shown here where the p value is falling in the rejection zone. Okay, it means you're going to be rejecting your null hypothesis. In both the cases, I'm talking about the right. That is the same scenario for your left tail test. All right. So, all right. So now the last piece of information is how are we going to identify the alternate hypothesis? So you will be given some kind of hint in your problem. If it is less than, then your problem will have the key saying less than, below, lower than, shorter than, smaller than, decreased, reduced. So these are all the keywords that you will see in your problem associated with the less than sign. And for the greater than sign, you will have greater, above, higher, longer, bigger, increased. So these are all the keywords that will associate with your alternate hypothesis. But always, so this is going to be always. In Math 130, your null hypothesis is going to be always mu equal to mu sub 0. So you are allowed to play only with your alternate hypothesis. It could be one of the three. All right. Suppose if you have the two tail test, then you will see the wordings like not equal to, it is different from, or has changed from, is not the same. So these are all the keywords that your problem will have, so that it will be easier for you to choose your alternate hypothesis. All right. So this is a tiny piece of information that I want you to learn for picking your alternate hypothesis from the word problem. All right, so my blah 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 is over, and you can go over and you can review the recipe. But once you do one or two problems, you will be good. So let's see the answer key testing of hypothesis on mu. All right. So again, as I say, if you click onto this PDF, you will get the empty worksheet. Yes. So if you click onto the PDF, it's coming. Okay. So if you click onto this one, you get the empty worksheet. You can download it and you can do the problems for learning better. Okay. This is the empty worksheet. Alright, so let's see the first problem. Maybe just the one page, one or two pages. Okay. Maybe just one problem. I don't know. It all depends on your understanding and the time. All right. Let's see. So, an herbal medicine brand contains amounts of the active ingredients in milligrams that vary normally from capsule to capsule. A quality control engineer assesses the whether the capsules of this brand contains. You see the keyword, right? Which is less. So let's keep that in mind. So this is my keyword less, and this is the keyword for my alternative hypothesis. So I'm going to be using the Lafayette test keyword for my alternative hypothesis, and that's going to be involving the Lafayette test. Okay, all right. So now the amount is of 10 milligram, and standard deviation is 1.5 mg. A random sample of 25 capsules. So you are picking a sample of 25, and you find that um, the mean, or you found out the mean or the average coming from the sample of 25 is a 9.2 mg per capsule. Now, what is your null hypothesis? What is your alternative hypothesis? That's going to be circled. So you are given four choices A, B, C, D. So as I said, you have the keyword less. So out of the four choices, A is the most appropriate one. The null hypothesis is always going to be mu equal to mu sub zero, which is going to be 10 mg, the number coming from the population. And the standard deviation is 1.5. Those numbers are given in your problem. So in the place of mu sub zero, I'm going to put the number as 10, versus the alternative hypothesis is going to be less than 10. Why? Because of the keyword given in my problem less, I'm going to choose my alternative hypothesis as 10. And this is what is going to be assessed, or this is what is going to be tested. So this word is going to be my claim. So this is my claim. This is my claim. So what is the claim? The claim is going to be the alternative hypothesis. Okay? Did you get it?
I got the same answer as you.
Yeah. So you have to read the word problem. So that's going to be the challenging part given to you. And out of the four choices, my null versus alternative is going to be the first choice. Mu equal to mu sub zero versus mu less than mu sub zero. All right. So let's see what is wrong with my other choices. So I'm going to ignore the other choices because this is not the correct one, because I'm clearly given less than, so this is going to be ignored. And this is also going to be ignored because this x bar is 9.2 coming from the sample of 25. That cannot be defined in my null hypothesis. So that way, that choice is also eliminated. That choice is also eliminated. All right, because your mu value coming from the population is a 10 mg, and the 9.2 is coming from the sample of 25. So that choice is also eliminated. And here certainly it is going to be eliminated because this number is your x bar value, and this number is again your x bar value. We are not bringing the x bar value in our null versus alternative hypothesis. Null versus alternative hypothesis is going to talk about the number coming from the population. So those that way every single choice is going to be eliminated. All right. Now, what is your Z statistic? So that's going to be the next question. So the Z statistic is going to be, as I said, you are going to be using the Z-score formula that we used in chapter 13, which is X bar minus mu over sigma over square root of n, or you can rewrite it as square root of n times x bar minus mu over sigma. So you plug it in, and you get your z-score value as a negative 2.67. What is the meaning of this? You are going to say that the sample mean 9.2 is about 2.67 standard deviations below the center. All right. So the sample mean 9.2, that is treated as the numerical value, and that numerical value is 2.67 standard deviations below the center. So that's what I have shown in my diagram. So the sample data of 25 observations or 25 capsules is giving you the mean, and that is a 9.2, and that I call it as the numerical value, and that numerical value is converted into my z-score, and the z-score number is a negative 2.67. And what is the significance of that number? From the center, that number is about 2.67 standard deviations below, which is very big, right? So I can accept all the values within 95 percentage or the middle 95 percentage, but this number has a very big z score, and that way, yes, we are going to be writing, because I did not ask you to compare the p and alpha because my alpha is not given in the problem. So in order to answer the question, I am going to complete the z score number, which is 2.67, and what is the p value. So let's just answer the question, okay? I'm not doing the entire process here. So how do you get the p-value? The p-value is, it is going to be normal CDF negative 8 comma negative 2.67, and that's going to give me the z-score, the p-value. The p-value is a very less likely number, which is 0.0038. That is the probability value. All right, I'm not given the alpha, so I'm not going to do the comparison. But even if I am given the alpha value as 1% or 5%, so this probability value is certainly less than 1% my alpha number or 5% my alpha number. So I am going to be rejecting the null hypothesis. I hope you understand my wordings. Since the probability value is a very less likely number, which is 0.0038, when I compare with this alpha as 1% or 5%, since my p-value is much lesser than the alpha value, I am going to be rejecting my null hypothesis. So this is what is going to be written, but since I am not given my alpha value, I'm just going to answer the question of getting the z statistic and getting the p value. With that, I'm done. So my goal here for the first problem is choosing the null versus alternative. Then they're asking me to get the z-score. I know how to get the z-score using the z-score formula that I studied in chapter 13. And then the next one is getting the p-value. So p-value for the left tail test, I know how to get that. Just complete it. That's what they are asking you. All right. So the same thing I am going to be showing how to get that using your TI. So now I want you to take your TI. All right. Maybe I did not do that with the TI. Maybe I did not do that with TI. So maybe and it's coming. Sometimes it's too slow. Sometimes it's too slow. All right. So now I'm going to write the recipe for my TI. So take your TI and then you are going to go to stat and then test. Stat and then test. Messy job here. I don't have room. All right. So go to stat and then test and then select option number 1, which says Z test. Option number 1, which says Z test. Z test. Select option number 1, which says Z test. All right. So I'm going to take my TI and I'm going to plug in the numbers to show you how to get the Z score using the TI and the P value. So here I wanted to go to stat, move on to test and select option number 1, Z test. I told you chapter 14 and chapter 19, the answers are on your TI. All right, so test and then select option number 1. So here, my input screen, I'm going to write very gently. Okay, so this is going to be the data. So the next one is stats. So this is what you will be seeing. Okay, I'm going to ignore the data because I'm not given the data of 25 observations or 25 capsules. All right, so the next one is going to be the mu sub zero. So the mu sub zero value is, what is that? It's going to be 10. Let me plug it in, the mu sub zero value as 10. So let me input the value as 10. Okay, move the cursor down and it's asking what is the sigma value. So the sigma value in my case is 1.5. So I'm going to be plugging in the number as 1.5. So 1.5 is my sigma, plugging in. Move the cursor down and it is asking what is the X bar value. So the X bar value from my data, it is a 9.2. So 25 capsules is giving the mean, which is 9.2. So plug it in, 9.2. Move the cursor down. And then it's asking what is the n value. N value is 25. Plug it in. N is 25. Plug it in. And then you see that there are 3 options. So one is mu not equal to mu sub 0. I hope you're all with me. Mu greater than mu sub 0. I'm just writing whatever the TI screen is going to show. So I am going to be choosing this option because my alternative hypothesis is mu less than mu sub 0. So these two are ruled out. I'm not going to be using these two. So bring the cursor to mu less than mu sub 0. And then you will see the color, which is not needed. And then I want you to hit calculate. Some people will have the draw. I don't know what calculator you are using. So I am going to hit calculate. Okay. So when I hit calculate, so this is what I would be getting, the output screen. So the output screen will say mu less than mu sub 0. And then my z-score is negative 2.666667. And then my p-value is 0.0038. 3042 4251, and then my X bar value is a 9.2, and then N value is 25. Are you all getting this?
Yeah, I got that.
I got it.
Yeah. So it's pretty simple. That's what I'm telling you. Chapter 14 and chapter 19 is easy peasy. Toward the end of the quarter, everything is on TI. You don't have to do anything extra. So your conclusion should be written, and that's about it. Choosing the alternative hypothesis is by reading the problem, you can pick your alternative hypothesis, and everything is on TI. Check, check, check. Plug in the numbers. Boom. TI is going to give you the z-score number and the p-value and everything, right? So that's what I showed by hand. So how the work is going to be done here, you see that it's by hand. All right. Any questions?
I think I'm good. That makes sense to me.
Yeah, so this is how it's going to be done. So just answer the question, what is a z-score and what is... So the recipe was kind of new to us, but when it comes to the problem, it's much better. All right, the next problem is your problem with the data. Okay, so the data values are given for 8 observations or 8 syringes, and your now mu value. So again, I'm telling you, reading the problem is important. Okay. So the first one, it says the company manufactures 200 insulin syringes designed to contain 1 ml, and that is the number coming from the population. So it is going to be mu equal to 1. Continue to read. So now you have that volume, the solution volume is set to follow normal distribution with mu, which is 1 from the previous center. sentence, and your standard deviation is about 0.05 ml. All right, now we randomly pick about 8 syringes, and the results are given below. That's right. So you have a tiny table with 8 data points. All right, so now let's answer the question. Do these data give evidence that the population mean solution volume is not 1 ml? So this is the hint for my alternate hypothesis. So what is the keyword? The keyword is going to be not 1 ml. That is going to help me to construct my alternate hypothesis. See, the alternate hypothesis is not equal to 1. All right. So what is the null hypothesis? So the null hypothesis is going to be mu equal to 1, obviously. And what is the alternative hypothesis? The alternative hypothesis is going to be not equal to 1. So now I told you that in my recipe, you have to identify the claim. Remember, I said I will talk about this later. So in my recipe, I have given you, you need to identify the claim. Sometimes your null hypothesis will be the claim. Sometimes your alternative hypothesis is going to be the claim. So that's what I told you here. It's coming again there. It's coming. Yes. So here you are going to identify the claim. So in both the statement, I said identify the claim, identify the claim. Sometimes your null hypothesis is going to be the claim. Sometimes your alternative hypothesis is going to be the claim. So basically, you have to look evidences for your claim. So that's what you are going to be seeing here. You are going to assess, or you're looking for evidences to test the claim about the population mean you. All right. So this is important. I have given that in my recipe. Okay. Now let me go back to the worksheet. That's right. So what is the now the claim? I am looking evidences to test the true population mean is not equal to. So that's going to be the claim, and that's going to be my two-tailed test. If it is not equal to, that's going to be my alternate hypothesis. Always the null hypothesis is going to be mu equal to. If you move on to the higher level of statistics, then you may work on the null hypothesis with the less than, greater than, not equal to sign. But this is just the introduction to your testing of hypothesis in Math 130. So we always stick with mu equal to 1. That is your null hypothesis. Or you can say mu equal to mu sub 0 is your null hypothesis. Your alternative could be one of the three. But in this problem, if I read carefully, I am choosing my alternate hypothesis as not equal to, because it says the volume is not 1 ml. That's right. So that's going to be the claim, and that's the two-tailed test, and that is going to be the correct choice. I'm eliminating the rest of the choices. Okay, those are inappropriate. That's not the correct one. They are not appropriate ones. Okay, and then what is the z-score? All right. So now I'm going to cheat. All right, because I'm not going to do my work by hand, because I know how to use the TI to get the z-score. So this is what you're going to be doing. Because the data is given, you are not given the sample mean, because you need the sample mean. Since you are not given the data, so I want you to plug in the data first. So that's what I have instructions here. So go to stat, go to the edit option, and then plug in the data in any one of the 6 columns given to you. All right. So in my case, I had the data in L3. So whichever column is available to you, so this is going to be done first, step number 1. Or you can say plug in the data. Plug in the data first. Right? So just make sure the data is available in any one of the 6 columns. Right? So I just entered all the 8 observations in L3. You can try this one. And after that, go to stat and then move on to test. Select option number 1, which says C test. And this time, yes, you had to be very careful. So the previous occasion, we ignored the data. Previous occasion or in the previous problem, I ignored data. I used stats because my X bar was given, the sample size N was given, every single information, was given directly in my problem. So I ignored the data option. But in this problem, since the data is given, I'm going to be choosing data, ignoring stats. So check, plug it in. Mu is equal to 1 and standard deviation is a 0.05. And once you switch to data, the screen is going to be different. Once you switch to data or once you pick the data option, it will ask the list. The list is nothing but your X data, and you have to tell where the data has been stored. So second L3, it will ask you the list. Then wherever you stored your data, remember to press second and then L3. I don't know where you are going to store your data. I told you that in my case, I have stored my data in L3. All right, so second L3, and then move the cursor down. It will ask you the frequency. The frequency is 1, which is default. Yeah, you don't have to change the number. And then move the cursor down. Again, you will get the 3 options. Mu not equal to mu sub 0, mu less than mu sub 0, mu greater than mu sub 0. So ignore the other 2 options and then use mu not equal to mu sub 0 because that's your alternate hypothesis. And then move the cursor down and then hit calculate. So the output screen will give you the z-score value and the p-value, the sample mean of 8 observations, and then your SX value. Obviously, the calculator will give you, when you plug in the sample data, the sample mean and the sample standard deviation, those numbers are going to be there, okay? Because they go like twins. Mean and standard deviation, they always go like twins. So once you plug in the sample data, it's going to give you X bar and SX value. Sample mean of 8 observations. So as much as I can, I have written all the information. Please sit with my work, go over, and then try to understand. Okay. Okay. So this is how we are going to be using your TI to choose your Z value. The Z value is the Z-score, which is 0.99. That Z-score is well within my 2 standard deviations, which is a negative 1.96 to positive 1.96. So as long as my Z-score is between negative 1.6 to positive 1.96, it's clear. I will never reject my null hypothesis. Only if my z-score value is above 2 standard deviations or below negative 2, then I would reject my null hypothesis as long as my alpha is 5%. Again, in this problem, I am going to be choosing, the p-value is a 0.332. They did not ask, but I have written that one. Maybe later it comes. Oh yeah, later it comes. In the E subdivision, it comes. What is the p-value? The p-value is 0.322. That's right. Because that was the p-value given by my TI, or you can also use the normal CDF. Normal CDF, which is 0.99, comma 8, and do not forget to multiply it by 2 because it is the two-tailed test. It is the two-tailed test. Okay? Take your TI and see, plug it in. So it's going to be 2 times. No, second was option number 2, 0.99, comma 8. So what do you get? It's 0.322. 0.322 1, 7, 4, 1, 2, 2, 4. So that is the probability. So that's what we got. All right. Anybody has any question?
I'm all good, thank you.
How about others? I still have few more students with me. How about others?
I'm good too.
Mm-hmm. Thank you. So, which is the appropriate diagram? Because it is a two-tailed test, I would go with the two-tailed test. The first one is the appropriate one, not the second one, not the third one, not the fourth one. Okay, because mine is a two-tailed test, so it's going to be on both ends. So this is the center. So this is the center mu equal to 1, and the corresponding z-score at the center is going to be equal to 0. Okay. All right. So now the next one, how are you going to write the conclusion? So again, for conclusion part, I told you that you are going to compare the p and alpha. Since your p-value is about 0.322, which is certainly greater than your alpha, and your alpha is given in the problem, the level of significance, which is alpha equal to 0.05. So it is given in the problem here. Alpha value is given in the problem, it is 5%. All right. So when I compare my p-value with alpha, my p-value is about 32% based on the sample data. My probability value is pretty strong, which is 0.322 or 32.22%, which is much greater than my 5%, my alpha. So I am going to conclude that there is not enough evidence to say that the true population mean volume is not 1 ml. That is the appropriate one because I'm going to keep my null hypothesis. Okay, so out of the two statements, one statement is mu equal to 1 ml versus another statement that mu not equal to 1 ml. So since my p-value is much greater than alpha, I fail to reject the null hypothesis. That means I'm going to accept the null hypothesis. Stronger the p-value, I fail to reject the null hypothesis. You can remember the recipe that I have given. If p-value is greater than or equal to alpha, if p-value is less than or equal to alpha, I reject my null hypothesis. I refute my null hypothesis. On the flip side, if p-value is stronger, if p-value is greater than alpha, I fail to reject my null hypothesis, right? It means I'm going to be keeping my null hypothesis, accepting the null hypothesis. But I don't want to write my conclusion based on the null hypothesis. I want to write my conclusion based on my claim. That's why I have to identify the claim. So according to the given problem, my claim is going to be mu not equal to 1. So that is the claim. That's what I call it as my two-tailed test. So I'm also looking evidences for my claim. Read the question. Does the data give enough evidence to blah, 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 blah? That's right. So I'm going to be writing the conclusion based on the question asked. So I am looking for evidences for this. Sorry, too much blah. Too much blah, blah, blah. All right. So does the data give enough evidence to the statement is going to be mu not equal to, and that's going to be my alternative hypothesis. So this is my alternative hypothesis. Alternative hypothesis is given by HA. Alternative hypothesis hypothesis is going to be my HA. So that HA is going to be my alternate hypothesis. So I am looking evidences for this one. So now I am going to be choosing out of the 4 sentences, which is the most appropriate one, the D. There is not enough evidence to say that the true population mean volume is not equal to 1. Or since the p-value is greater than alpha, this part is tricky. You have to understand the final conclusion that I said. Smaller the p-value, reject the null hypothesis. Stronger the p-value, fail to reject the null hypothesis. Keep that in mind. Also, your problem says, does the data have enough evidence to, right? So based on the question asked in the problem, this is going to be your conclusion, and out of the 4 choices, the 4th one is the appropriate one. I have written every single information to choose your alternative hypothesis as your claim. Okay, so again, the technical definition or the technical way of writing the conclusion is you are going to keep your head sub 0 because of the strong probability, but you don't want to say anything about your null hypothesis. What you need to say is you are going to say the conclusion about your alternative hypothesis, because that's what is going to be tested and that is your claim. So your alternative hypothesis is going to be rejected. So when you are going to be rejecting the alternative hypothesis, that's right, is going to be the 4th choice. All right, and then yes, so these are all the multiple choice question. So multiple choice question has 4 options. So which of the following would be the strong evidence? So which one is going to give you the strong evidence against the null hypothesis? So you have using a smaller level of significance? No. Using the larger level of significance? No. Obtaining the data with a smaller p-value, you have strong evidence to reject the null hypothesis. That's what the conclusion part in your recipe says. Smaller the p-value, you reject your null hypothesis. So that is the most appropriate one. Okay, so in that way, these are all the incorrect. Okay, so I will start with the first 2 questions, and maybe you can just go over the material. The rest of the packet I can complete it tomorrow, or you can also sit with the packet with the answer key and try to understand. Okay, unless you put your mind to this concept, it doesn't make sense. You have to understand the recipe given in testing of hypothesis. You have to understand every single word given in your problem, and above all, you need to put your mind to this kind of concept. Only then it will make sense to you. Otherwise, everything is going to be hazy and you will not get anything out of it. All right. Okay, so the next one, the head subdivision, with that I am done. Okay, so in testing of hypothesis, what is the significance of, or what does the p-value tell us? So it's going to be, again, out of the 4 choices, the p-value tells. Again, the same question is interpreted in a different way. What is that? Smaller the p-value, you are going to refute your null hypothesis, or your null hypothesis is going to be rejected. So again, the same concept, but with the different wordings, you are asked in your multiple choice question. Okay, so in I have given that one here in my recipe. So I'm going to go back to my class notes. The bottom I have given. It's coming. Yes, here it is. So that is the definition of your statistically significant. So what is the definition of statistically significant? Less likely p-value, rarely occur, is going to be called as, that means same as your less likely p-value or smaller the p-value, it's going to be called as statistically significant. That is again the technical term that we are using here in testing of hypothesis, which is nothing but smaller the p-value. Okay, p-value is less than alpha, then you reject your null hypothesis. That's what we call it as statistically significant. Less likely p-value or smaller the p-value. Or the smaller the p-value. All right, so I let you guys go, and tomorrow we will meet again and we will discuss one more time about the testing of hypothesis, and we will also complete this worksheet. That way you will be good. Chapter 19 is going to be pretty easy once you have the concept on chapter 14. Only the difference is it's meant for quantitative variables. Chapter 19 is going to be about the qualitative variable, but it's going to be pretty easy. Okay, so tomorrow we will finish the packet, page 2, page 3. There is only 4 pages, and your homework problem on sapling learning is going to be similar to this. But still, if you have any question on the sapling learning homework on chapter 14, check with me. Okay, so tomorrow I should be completing chapter 14 on testing the hypothesis. Okay. So please spend some time in going over the answers, because every single question has the answers, and there are only about 11 questions. So you can easily work with these 11 questions to get the idea of testing of hypothesis. Sounds good?
Sounds great to me. Thank
Sounds
you.
good.
Okay, so before I say bye-bye to you, if you have any question, I can take your question. Otherwise, I can also check with you tomorrow. How about that? Anybody has any question?
Do you know, off the top of your head, when this week's quiz will be?
Before your finals, everything is going to be 14 and 19 is going to be one quiz, and that's going to be on Wednesday.
Okay, so there's not going to be there's not going to be like a chapter 15 quiz. It's just going to be for 14 and 19.
14, 15, 19. Sorry, 14,
Okay, that's
15, 19 is going to be one quiz, and that's going to be right before your finals.
Next week.
Mm-hmm.
Awesome. Thank you.
Mm-hmm. With that, you're done. So 14,
Okay.
15, 19 is going to be one quiz with the 20 questions, and with that, you're done. And then finals is
sounds
also going to be next week. That's right.
Right.
August 13th. Everything is going to be, back to back to back. It's going to be kind of hectic. But with that, we are done.
Okay, sweet. Thank you.
Yeah. All right. Okay. Bye-bye.
Thanks so much, Ms.
Bye bye.
Paula.
Thank you.
Bye, thank you.
See you. Bye-bye. Bye. Have a nice day.